This is the 10th lecture in our series on net zero. And I have to confess, it's the lecture I didn't want to give because it's the lecture kind of everybody tends to lead with. And I worry about the whole tipping point discussion around climate.
The Gresham College lecture that you're listening to right now is giving you knowledge and insight from one of the world's leading academic experts. Making it takes a lot of time, but because we want to encourage a love of learning, we think it's well worth it. We never make you pay for lectures, although donations are needed. All we ask in return is this: send a link to this lecture to someone you think would benefit, and if you haven't already, click the follow or subscribe button from wherever you're listening right now. Now, let's get back to the lecture.
It tends to be when I tell somebody I'm working on climate, if the next thing they say isn't about low traffic neighborhoods, which it quite often is, it's often about, is it true that some tipping point is about to happen or has already happened and we're all doomed? This is one of the reasons. There's an obvious reason why tipping points are dangerous. It's a very bad idea to push our planet over a tipping point into some completely unexplored climate regime. So I'm not, the reason I was sort of hesitant about giving this lecture is I absolutely don't want to give you the message, nothing to see here, there are no tipping points, don't worry about it. But at the same time, there's a very unhelpful narrative around tipping points that I think is out there in the climate conversation. So it's quite a difficult one to balance. We have to take them seriously on the one hand, while at the same time not allowing ourselves to be sort of blinded in the headlights, which is the other sort of part of the other danger with thinking about climate tipping points. I'll give you some examples, and we'll do some maths. I am a physics professor, as you know, so there will be equations. There are for the newcomers. I'm afraid there won't be any equations done with hydraulic models. Although if you want to see our hydraulic model, particularly when it went wrong as well, and I start swearing on screen, it's all there on YouTube. I'll finish up by talking about how we should get our response to the danger of tipping points right. But I wanted to start with the danger of tipping points that people don't normally talk about or don't perhaps appreciate, and kick off, unconventionally therefore, for a lecture on tipping points, with Dana Nocitellis, I hope I pronounced that right, columnist in The Guardian, who a few years ago came up with the 5 stages of climate denial. And in the opening lectures of this Gresham series, we've addressed, the challenge of people saying that there is no problem. Yes, there is a problem. Denying that we're the cause. Yeah, I've explained in earlier lectures, pretty clear evidence that we are the cause of what's going on. In the last lecture, where we talked about the impact of climate change on weather, particularly in our part of the world, we were addressing the increasingly prevalent view among some in the political classes that, yes, climate change is happening, but don't worry, it'll be fine. And actually, all the things we might want to do about it are going to be so expensive, it's really not worth it. The next stage is denying we can solve it. Here's a headline I found just looking around. I'm sure Tessa Schlesinger, she's an authoress, and so I'm sure she'd be delighted for me to publicize what she writes, but this is the kind of headline that is really, really unhelpful. It's too late to stop climate change. Now we must decide what we can save and how we can save it. That's, I hope you'll realize, those of you who've been to these lectures, the kind of headline that really grinds my gears. Because, is she sponsored by Exxon? What's going on here? You can see who benefits. Ask yourself when you see a headline like that, who really benefits from this headline? Obviously it's attention grabbing, it gets retweeted and so on, but it's obviously unhelpful. But finally, there's another headline, the sort of "it's too late" headline, which brings us to the tipping point theme of this lecture. Here's a headline, Tony Blair. Blair warns of climate change tipping points. Tony Blair will warn today that the world will reach catastrophic tipping points of climate change within 15 years unless serious action is taken to tackle global warming. Anyone, any idea when this, this article has a yellow label on it. This article is more than 17 years old. So that was from 2006. And that's the danger. You can't say this that often before everybody starts going, oh, wait a minute, they've said this before, haven't they? So the first point to make in a lecture about climate tipping points is, and I should stress, this lecture is about global tipping points, the kind of tipping points that really grab the headlines, that would affect everybody all over the world, would affect the entire planet were they to happen. Obviously, there are other tipping points, local tipping points, a riverbank being breached, that's a tipping point, classic case of a tipping point. That could be, if it happens to be the bank that keeps the river out of your living room, then obviously that's very important for you, but it's not global. So I'm not talking about local tipping points or thresholds being exceeded, for example, in coral reefs and so on, which have an important impact for globally relevant, globally important species, but not necessarily a global impact on the entire planet. So we're talking about global tipping points here. And so the first thing I want to stress is, so far, there's no evidence of these things happening yet. And I stress the word yet there. Climate change has been really quite surprisingly predictable. And this is a figure from a report by William Nordhaus, the economist who won the Nobel Prize for his work on climate change economics a few years ago. This was published in 1977, and you'll see here that line, which I'm sure he drew by hand, shows global temperatures up till that point. They were going down at the time. In fact, Time magazine had a cover about the oncoming ice age, or People magazine, maybe one of them. But they did know that carbon dioxide concentrations were going up. And thanks to the work of Suki Manabe and Klaus Hasselmann and others, they knew what that meant. And we've gone through in these lectures what that does mean. And so he was able to solve, and this was the first time anybody had actually attempted to make a prediction of the time evolution of the coupled climate economy system. And I'm sure he used a computer the size of a room to do this. This was back in the mid-1970s. And he calculated the dashed line there. And that's what he predicted. And this is what's happened. It needs updating here. This goes to a couple of years ago. The blue temperatures are what Bill Nordhaus conceivably could have known about, but in fact he didn't, because we didn't observe global temperatures nearly as well then as we have done since. And the red, of course, is after he actually published his paper. And if we sort of use the magic of PowerPoint to slide it over, you can see he nailed it. He predicted we'd get to 1 degree in this past decade. It's exactly what happened. You'll also notice, by the way, that he predicts it accelerates around now, and that we get to 2 degrees around mid-century. But to reassure you, this was a prediction made by Bill Nordhaus, assuming that the world economy and the world population grew in the way they were projected to grow in the 1970s. And you may recall one of the things I remember as a teenager, lots of articles about the population boom and the fact that we were going to be 10 billion by whenever. So of course, one of the great good news stories of the past 30 or 40 years has been the fact that the world population is not growing in the way that it was. And of course, we have made perhaps some progress on decarbonization as well. So we're not predicting that rapid acceleration, but other than that, that's the future prediction from his. The world has warmed pretty much exactly as expected. And interestingly, perhaps surprisingly, in the standard models that we use for predicting climate change, these are the models used by the Intergovernmental Panel on Climate Change, it's actually surprisingly linear. We call it a straight line response. If you crank up greenhouse gas concentrations, you can see the yellow lines there, all the way up to 4 degrees, 5 degrees and beyond. The temperature is just following rising greenhouse gas concentrations. So it's a very, very simple prediction. And in the blue lines, which are a scenario in which we manage to stabilize greenhouse gas concentrations and start them declining again, you can see that they respond, again, very predictably. So there's no evidence in these models of anything that you would associate with a tipping point, like the planet sort of going up like this and then suddenly lurching into a new state. But, are these models miss a lot of the physics. They're quite coarse resolution. They don't have nearly enough variability at small scales in them. So there's plenty they could be missing. And there is a question we have to ask ourselves, are they too reassuring? And plenty of thinkers in this space strongly believe that they are. And this is the kind of tipping point narrative that many of my colleagues in academia do talk about a lot and worry about a lot. And this is the idea that, we are, and this is a nice figure from a paper by Will Steffen, which contains a lot of very sensible thoughts in it, but a lot of it is around how do we avoid these tipping points, how do we navigate the next few decades to avoid, pitfalls here, pitfalls there, and so on. And clearly the sort of choice they're sketching out here is that, we have to get on this Earth system stewardship pathway to avoid going over some planetary threshold and having the world run away from us into this hothouse Earth that they're worried about. So there's plenty there, and there's plenty of processes that are not well represented in our current models that could result in tipping point, globally significant tipping point behavior. Here's again a figure from their article which highlights the main tipping elements. These are parts of the climate system that could tip over, could suddenly. I suppose I should have started off by saying what I mean by a tipping point, because I'm just kind of assuming everybody kind of knows what I'm talking about. But so when you're Tim Lenton, who does a lot of work in this space, he uses the analogy of a chair. If you're sort of tipping a chair over, and eventually it'll reach a point where it'll fall over. Okay, so that's the analogy people have in their heads. It's not the same as sometimes people talk about a system reaching a tipping point, just meaning it's accelerating. And that's not what I mean. I mean, it's something much more, and I'll explain in a bit more detail what we mean by this sort of behavior in physics. An acceleration is not an indication of a tipping point. It depends what's driving the acceleration. It depends on the nature of what's happening. So, for example, the world is warming at its fastest rate ever at the moment, as we emphasized in a couple of lectures ago. But the reason for that is because the combination of greenhouse gas concentrations in the atmosphere that we're putting in is going up. If you add up carbon dioxide, methane, and also the progress we're making on reducing other forms of pollution which were keeping the planet cool, if you add all that up, it's driving that warming. It's not that the system has crossed some boundary and is suddenly moving into a new behavior, it's just that we're pushing it really hard. So that's why it's going fast at the moment. But these are the parts of the system which we worry about, which could display this threshold behavior where you push the system along and then it falls over and goes into a completely different state. One we'll talk about first is the thermohaline circulation. That's the global ocean overturning circulation, often associated with the Gulf Stream, but it's not the same as the Gulf Stream. The Gulf Stream is a surface current in the Atlantic, which moves temperature around at the surface, in the surface waters of the ocean, moves heat around in the surface waters of the ocean. But beneath it, there's a much bigger current, which is the entire ocean, this conveyor belt carrying water northwards through the Atlantic, sinking in the Arctic and returning at depth, which both have an enormous impact on our climate, and it's the thermohaline circulation that I'll be talking about when we come to talk about tipping points. We'll also talk about the ice sheets, the West Antarctic ice shelf, and the Greenland ice sheet, which again are one of the systems in our planet that we are monitoring and concerned about crossing some irreversible threshold. And finally, the Amazon rainforest, again, which is another big part of our planet that we are monitoring and concerned about the possibility of it being pushed over an irreversible point. But we'll start by talking about the thermohaline circulation, which is the one, it was probably the first big tipping point to be discussed extensively in the climate community. It's also the one where I'm most familiar with the processes involved, so I'm sort of most comfortable talking about it. And it also gives me a chance to remind those of you who were at my earlier lectures of things you've already heard about. So I can ask you. I won't call out the audience here. But if you were at my third lecture last year, where we talked about the ocean physics behind net zero, there's a few people looking slightly nervous. Is he going to pick us out here? And I was spent quite a lot of time in that lecture talking about why the deep ocean is so cold, why we have this very constant temperature in the deep ocean. And the answer I explained to you was because the water that gets into our deep oceans gets there from very cold places. Over most of the ocean, the surface waters are too warm to mix with the waters beneath them because they're warmed by the sun, they're less dense than the water underneath them, so they can't mix. They just slide around over the abyssal waters. And the only way water can get from the surface layer down into the deep ocean is through these relatively isolated regions of so-called deep water formation, which are highlighted in this graphic near Antarctica and in the North Atlantic. And the reason the water can only sink down to ocean depths in these regions is because of the reason water can sink down to the ocean depths in these regions is because of the peculiar equation of state, the equation that determines the density of seawater, and the fact that as you cool water down, it gets denser and denser and denser, but then it stops getting dense. You remember we emphasized this as you're cooling water towards zero. Eventually it stops getting dense. And of course, when it freezes, the ice floats, so it sort of becomes less dense again. So there is a point at which water is no longer, the density of water is no longer as sensitive to its temperature and becomes sensitive to other things. And it's in particular the salt content of water that determines how it escapes down into the ocean depths. So crucial to this story, therefore, now we're going to, in that lecture, in the Ocean Physics Behind Net Zero, we kind of just mentioned this as something going on which it helped us explain why there were two timescales in the planet's response to rising greenhouse gases. We had the sort of surface warming and then this very gradual warming of the ocean depths. But we kind of took this ocean conveyor as granted, as just something that was happening and determined how the system responded to rising greenhouse gases. But now we're going to ask ourselves a bit more about what drives it, what controls it, and could the conveyor itself be disturbed by what's going on in our surface climate? So here's the question: what are the controls of that great ocean overturning circulation, the thermohaline conveyor? And on the one hand, we've got accelerators, things that make it go faster, which is, for example, the fact that polar waters are colder than equatorial waters, which makes them denser. I mean, even so because equatorial waters are much warmer, so their temperature does matter at those temperatures at the surface, and so you have the cooling of polar water, the fact that the poles are colder than the equator, is essential for this overturning circulation to be set up. We also had, and I emphasized this in the ocean physics lecture, that evaporation and ice formation in these cold regions makes water saltier, and therefore that also makes the water denser and allows it to escape down into the ocean depths. But on the other hand, there are brakes on this overturning circulation. And the most obvious one is just, as it were, friction, like any conveyor belt. It's got to overcome friction. The friction we're talking about here, because it's a fluid and it's on very large scales, it's actually really mostly the role of eddies in the system. So interestingly, when you try and model the behavior of the ocean on very large scales, you have to model it almost as quite a sort of sticky, syrupy substance, because you're not resolving all the little eddies that actually slow it down. We digress slightly here, but you've probably noticed this. If you're trying to suck water through a straw, if you suck it slowly, you don't have to suck very hard. But if you try and suck really quickly, you'll notice suddenly it becomes much harder to get the water through the straw. Okay, do try. Don't choke yourself doing this. But what you're seeing there is the fact that as soon as the flow through the straw becomes turbulent, it actually the resistance to the flow goes up a lot, very very rapidly, and so turbulence in the ocean slows down this overturning circulation. So that's one thing, one sort of break we've got on this overturning. But the other really important one is the fact that it's not just evaporation and ice formation that I talked about in the last lecture, that's the lecture in the oceans lecture, that matters in these polar regions. We also have precipitation. We have rain, snowfall, and so on, which is fresh water being added to our Arctic oceans. And of course, ice melts as well, both sea ice and also ice on ice shelves and ice caps. And that injects fresh water into the polar regions, making it fresher and therefore making it less dense and therefore slowing down the formation of deep water. So you can see it's the balance between these two things that determines how strong the ocean overturning circulation is. And I've highlighted the precipitation one because that's the one where we believe things may be happening which may be affecting the strength of the global overturning circulation. Because if we look in those climate models, and these are the same climate models that gave us that very linear, boring, warming response to rising greenhouse gases that I showed you, this is what happens to precipitation in those models. And you'll notice that in the Southern Ocean, in these regions where there are important deep water formation regions around Antarctica, precipitation is predicted to increase a bit, 10, 20% or so. And there's no sort of hatching there, which means the models are pretty much in agreement. 80% of models agree, as it were, that there will be an increase in rainfall in those regions. In the North Atlantic, you'll notice the colors are a bit washed out, so it's kind of around zero. But you'll also notice there's lots of diagonal lines. So we really don't know what's going to happen in the long term to precipitation in the North Atlantic. By the way, because somebody's bound to be wondering, you'll notice that the UK is blue and there isn't, so I'm sorry, the consensus is pretty clear in the models that the UK is going to get a bit more wet and miserable. Anyway, but we're talking about the global picture here. And a long time ago, Henry Stommel introduced a model of this process, the overturning circulation, and how it might depend on these external drivers, that actually captures the essential sort of conceptual ideas of the whole tipping point, ocean tipping point discussion. Henry Stommel was very, very interesting. He died, I think, in the 1980s or 9 maybe. But but he was one of the great oceanographers of the 20th century. And one of the last ones, he never did a doctorate. He was a craftsman of the oceans. And he understood the oceans. He did a lot of very, very fundamental work on the basic processes that govern our ocean circulation. He's probably most well known for explaining the abyssal circulation, the sort of circulation of the deep oceans, which of course we were only learning about from very deep long line observations, and of course the submarine movements and so on after the Second World War. We were sort of discovering about our deep oceans. The work of his, which I wanted to talk to you about today, was his idea of a very simple model of the global overturning circulation. So you just imagine the world is just two boxes, an equatorial sort of rest of the world box and a relatively small polar box. And you've got an overturning that's driven by the density difference between the water in the polar box and the water in the rest of the world. So the water in the polar box is less salty than the water in the equatorial box, because in the equator there's lots of sun, lots of evaporation, water is relatively salty. In the polar box, lots of rain, lots of freshwater input, so it's less salty, but it's also colder. Put these two things together, the water there is, on average, denser than it is in the equatorial box, and therefore you have an overturning circulation. And it's steady because there's some friction. It doesn't just keep accelerating as it would if there were no friction, but you've got those important eddies doing the work to control it. Now, suppose if imagine the overturning strengthened, that would carry more water into the polar box faster, and if the amount of rain that was raining in the polar box stays the same, then the polar box gets saltier. Yeah? And that actually reduces the difference, so you have sort of higher salt, so it reduces the difference of salinity, reduces that resistance to the overturning that's introduced by the salinity. So the salinity in the sort of starting picture, temperature's driving the overturning, and the salinity contrast, the salt content contrast between the polar box and the rest of the world, is actually acting in the opposite direction, because the salt content here is lower than the salt content here, so it's actually acting as a brake on the overturning circulation. But if you strengthen the overturning circulation, you weaken the salinity brake, yeah, because you actually add more salt to this region. So you don't necessarily, it doesn't mean that, it all falls to bits immediately, but you can see immediately that, there's something interesting there, because there's a feedback between what any change in the circulation affects the thing that's also driving it. This is the sort of hallmark of a non-linear system where a change actually feeds back on itself. So there's a feedback there. And of course, if you have weaker overturning, you then have more fresh water getting into this. So the balance between water flowing in from the equator and water coming in from the rain is such that it ends up fresher, therefore less dense, and that has the opposite effect. And of course, if you reverse the overturn, this is crucial in Stommel's model, is that if you reverse this whole overturning, then you have exactly the same flow of salt into the polar box. You have the same setup, but you have even lower salt there because this is much weaker circulation. So let's sort of think about what this model means with a few very simple equations. So we'll call the overturning strength Q. That's the flow of water measured in something called a sphere-drup, which is a sphere-drup is a square kilometer of water moving a meter. So it's a unit for a flow of rather a lot of water. So if you did this in liters per second, it would be so sphere-drups is a better unit to use. We've got the temperature contrast, delta T. I use deltas to indicate temperature differences here. And it's from low to high. So delta T is positive. Yeah. So that's the difference in temperature between pole and equator, or pole and tropics. And then we have the salt contrast as well. Remember, you're starting off from conditions where the poles are always less salty than the equator. That's not predicted to change. So delta S is always positive as well. Again, we're setting this up so that all the symbols are positive to make it easy for you to follow. So, a couple of equations, but bear with me. They're very simple ones. The rate of overturning, if it's driven by the density, is proportional to, so these are just constants, A and B, there's numbers. It's proportional to one term which depends on the temperature difference, which is positive, that's driving the overturning, and another term which is negative, which depends on the salt content difference. So that's slowing it down. So it's the balance between these two which gives you the strength of the overturning. We've also got what determines the salt content. Well, we've got this continuous freshwater input, called E. There's an extra freshwater going in, and that's balancing the salt that's being carried in from the equatorial box, which obviously depends on the salt content difference. If that difference was 0, then the overturning wouldn't change the salt content, wouldn't transport salt into the polar box. Okay, but because there's always a difference between the equator and the pole, the stronger the overturning, the more salt it carries into the pole. These vertical lines here mean it doesn't matter what the sign of the overturning is, that's always positive. So what we call modulus sign, okay? And that means that it doesn't matter whether it's mixing it that way or mixing it that way, it's the amount of overturning that determines that the size of this mixing in of salty water into the poles. So those are our two equations. They're the only two equations in this lecture. So if you hate equations, you've made it. We've got past them, and we can now talk about what they mean. If we just rearrange things, this is the same equation. Okay, just before, in case you get suspicious of me. He said there was only two, but no. This is, I have actually stuck with the promise. Hopefully you can see that I'm just taking this equation and plugging it into that one, and I say that the rate of overturning is just some constant, that's the overturning we would get if the salt wasn't doing anything at all, minus this term which is proportional to 1 over the rate of overturning itself. And, if you go away and somebody's shaking their heads as if, he's trying to bamboozle me. But you can rearrange this equation and get to that equation fairly straightforwardly, and encourage you to go and do this. We can simplify it even further. And again, I'm just rearranging here. You can see I'm just dividing by Q0 and introducing a new little symbol, delta, which is just, a combination of these constants. And this boils the thing down into a single, very, very simple equation relating Q to something which is 1 minus a constant divided by the size of Q, the modulus of Q. So I'm saying if the overturning is in equilibrium, that's what determines that it satisfies that equation. And as I hope you can all remember, if you've got an equation which relates sort of one thing and another thing, you can draw a graph. And you can see that you've got, this is straight line here is Q on Q0. That gives you a straight line because as you go, it's just proportional to Q. And then these dotted lines here are proportional to 1 minus delta on the absolute value of Q. And so 1 over Q gets big when Q is 0. Yeah? So 1 minus 1 over Q disappears into the floor. Yeah? That becomes infinite when and so you can sort of see why the dotted lines are the shape they are, I hope. And the fact that it's symmetric is because this is the modular sign. It doesn't matter whether Q is positive or negative, the dotted lines are the same on both sides of 0. So that's where we are now. So I hope you'll realize it was worth it going through this equation because it helps us understand the whole principle of tipping points here. This is where we are now. If the dotted line, I haven't left myself enough time to explain in detail why, you'll be pleased to hear. So if the dotted line's above the solid line, so if we disturb where we are now, if the dotted line's above the solid line, it's pushed upwards, it's pushed towards higher Q. And if the dotted line's below the solid line, the system is pushed towards lower Q. So where we are now, if it sort of wobbles around a bit, it's sort of pushed back to where it started, yeah? So it's stable. Took me a lot of PowerPoint to do that, so. Okay, but what if it rains more? What if, those models are saying it's going to get wetter in the polar regions, and so that freshwater input goes up, and if you remember this delta term, one of the things feeding into it was that freshwater input. It was a combination of various variables, but one of them was the freshwater. So suppose delta is increased. So I'm going to go for, it was so good. Let's see it again. Okay, so those were just random variations. So at the moment it's stable. It's not as if a simple fluctuation from year to year is going to suddenly send the whole thing haywire. But suppose we had a systematic increase in precipitation. Okay, so you can see I've increased delta from 3 to 4. You can see that the dotted lines move downwards. Yeah? Because delta increased. Okay. And then eventually you're going to get to a point where the only way it can go is down. So as we increase the precipitation, we're pushing down the dotted line. Yeah, it's 1 minus delta over Q, over mod Q, so as you make delta bigger, it's pushing it downwards. And as I push it downwards, you can see the overturning weakens, it moves towards 0, okay? And eventually you get to this critical point where the dotted line only just touches the solid line. And remember, if your blue dot is on a place where the solid line is above the dotted line, it moves to the left. And so if we go just one tiny bit further than that, it can't stay there at all, and it has to drift all the way off down. It has to very suddenly transition off down to this other side of the regime, we call it, this other ocean state, where the overturning is now negative, so it's reversed, and it's much, much weaker. It's a small, weak, negative overturning. And we have a completely different climate state. And that would have very dramatic consequences for climate, certainly in Northwest Europe. So these are the amount in a recent study led by a Dutch group looking at the implications of this. They found that certainly in the vicinity of Bergen, you could have a reduction of over 15 degrees in the course of a century. So here we are, here's showing in various cities. Bergen, you can see, is the pale blue one, which drops very rapidly at the point where the thermohaline circulation collapses. And of course, this gives you cue dramatic film scripts. We could digress on all the physics they got wrong in The Day After Tomorrow, but the basic the basic premise of the film was that this happened, and therefore you suddenly had this. Now, it's important that in those models that I showed you, the sort of standard climate models, we do see a weakening of the overturning circulation, but it's not, in none of them does it look like this over a cliff scenario. The overturning circulation's getting weaker. It does have some climate impact, but it's not showing this tipping point behavior. But that's those models, and there are cases, if you, with the right experimental setup, if you deliberately dump lots of fresh water into the North Atlantic, you can eventually drive one of these models to go over a cliff and transition to a completely different state. So this is a case where you can see the thermohaline circulation is trundling along, and then they start pumping in fresh water, and after a few hundred model years, it suddenly goes over a cliff, and you get that sudden transition behavior. And what's happening in this model, this is a very complicated model of the whole Earth system, but the essential physics of it are pretty much the physics I explained to you from the Stommel model. That's essentially what's going on there. Now, and there is some evidence that this has happened in the past. So, the paleoclimate community, the ice core community, love to plot time backwards So older is over here and younger is over here. So sorry about that. But flip this around in your head. So moving out of the last ice age, you can see that temperatures were warming. The pink line is temperature in Greenland. Temperatures were warming, and then very suddenly, dramatically fell off, well, on a couple of occasions, fell very rapidly back down to ice age conditions, and then even more suddenly recovered and popped out of the ice age again. And this is called the Younger Dryas event. And there's a pretty good theory. I'm sorry to say that paleoclimatologists don't seem to agree on much. So although I think it's a great theory, there's plenty of people who still sort of grumble about it. But it comes from Wally Broecker, another of the greats of 20th century climate science. And he pointed out that as the Laurentide ice sheet, this ice sheet that covered North America, was retreating, it created, just the presence of the ice, created a massive lake called Lake Agassiz, which no longer exists. But it was a bigger lake than all of the Great Lakes combined, trapped by the ice sheet as the ice sheet was retreating. And at some point, of course, the inevitable happened. The dam burst, the ice dam burst, and all of the water in Lake Agassiz drained out down the St. Lawrence Seaway into the North Atlantic. And that would give you the kind of very sudden influx of fresh water that you would need to potentially suddenly shut down the ocean overturning circulation. So this is the theory, Broecker et al. In 1989, and it's been sort of confirmed in a few other papers since of why that Younger Dryas event occurred. There's lots of other papers. Every time somebody publishes papers saying there's evidence for this, somebody else publishes a paper a few months later saying, yeah, but the dates aren't quite right or whatever. Anyway, but they argue about it. But it's a great theory, and it's quite a plausible theory as well. So here's the question. What do you see? That's the Atlantic meridional overturning circulation. That's the state of the ocean conveyor at the moment. Yes, it's gone down, and it's gone down significantly in this period we've been observing it over the past 30 years or so. Is it heading for a tipping point? I'm afraid I can't tell you. But it's moving in the direction that we would expect it to move in response to freshening of the North Atlantic and so on, all the things which we believe going on. So that's the situation we're on that. I'll just skate over a couple of other examples of tipping points. I won't, that gives you, I wanted to go into detail on one of them so as to give you a gist of how it actually works. But just sort of for completeness, there's the ice sheets in Greenland and Antarctica. These, of course, there's scope for instability in the Greenland and Antarctic ice sheets because, I don't know if you know this, but much of the altitude of Greenland and Antarctica is provided by the ice itself. And in fact, if I take away the ice, that's what they would look like. So you can see that, in particular, West Antarctica and central Greenland, without the ice, would be sea level, below sea level. And so one thing you can be sure about is if the ice were gone, it's gone. It can't grow back because, or it would take another ice age for it to reform, because once you've removed the ice, you've actually lowered the surface of the Earth, in effect, as far as the atmosphere is concerned, and made surface conditions that much warmer. So there's obviously scope for a tipping point there, and we are seeing, very importantly, significant loss of ice in both Greenland and Antarctica, and this is from gravity measurements that NASA's been performing ever since 2004, and we can actually see the weight of the ice sheet from the gravity measurements they make with satellites. We can see the mass of ice changing in both Greenland and in particular in the West Antarctic ice sheet, which is, again, one which we're tracking closely because, of course, these are the points where the ice sheets are potentially most unstable. So Greenland is losing about 250 billion tons of ice per year, while Antarctica is losing about 150 billion tons of ice. Those sound like extraordinarily large numbers. They are. And again, I wouldn't want to belittle the importance of what's going on here, but I think it's also important to get these numbers into context. So 270 billion tons from Greenland, 150 billion tons per year from Antarctica, that's in the context of total mass. So these numbers often people don't put together. Total mass of ice in Greenland, 2.7 million billion tons. Okay, total mass of ice in Antarctica, 24 million billion tons. So if it carries on at the current rate, Greenland will be gone in 10,000 years. And Antarctica will be gone Antarctic ice will be gone in 160,000 years. Now look, of course, we're worried not about it carrying on at the current rate, but about the possibility of it accelerating. But at the same time, when you see the headlines about the speed of melting of Greenland and Antarctica, it is important to put those into context. There's a lot of ice there. And so we are aware of the possibility of pushing the system over a tipping point in the cryosphere. And of course, the big danger with pushing the system over, so the cryosphere is our name for the ice systems of the world. And the danger, of course, of once you've pushed the ice systems of the world over a tipping point, it'd take a very long time, but you wouldn't be able to get it back again because, ice dynamics is so slow. So this is, an area of concern for, collapses in ice sheets are, at the moment, in current models, not predicted to have a big impact on sea level rise this century. But again, we're discovering all the time that the ice sheets are more dynamic than perhaps we thought they were. And so it's an area also that the scientific community is monitoring very closely. Finally, tipping points in forests. One of the concerns in Amazonia is that the rainfall in Amazonia is sustained by the presence of the forest itself. And so you've got, again, just as we had with the overturning circulation, where there was an interaction between the circulation itself and the forces that were driving it, there's an interaction between the presence of the forest and the rainfall that sustains the forest in the first place. And we are seeing drying out. So wherever you see red and orange in this, we're seeing reductions in soil moisture over Amazonia over the past few decades. And we're seeing, in particular, incidents like a drought that occurred just last year. So you can see it's the same image, the same location. In just a few months, you went from that to that when rainfall was essentially ended in a large chunk of Amazonia. So people are worried about the possibility of pushing Amazonia over a tipping point. But this is one of the ones where, when it was initially proposed back in 2000s, it actually had a very unfortunate consequence of many people in Brazil saying, well, if it's all doomed anyway, bring on the chainsaws, because we may as well make some money out of this while it's still there. Okay, so it's very important to emphasize that most of what's happening in Amazonia is nothing to do with climate change. Yes, climate change is contributing something to what's going on, but Amazonia is, please take note, Amazonia is not already doomed. And there's therefore no logic to saying, oh, well, we may as well exploit it while it's there because it's going to be gone by mid-century anyway. And that's an example of where, talking about tipping points can get dangerous. And just to sum up, the things that I worry about, the reason I put off talking about tipping points for so long in this lecture course is I feel it can encourage fatalism. You can think, oh, well, we're doomed anyway, so what's the point? And we do need, it's not to say tipping points are not important, we do need to understand what's happening, and of course the further you stress the system, the more likely it is you're going to encounter one of these tipping points. But it's certainly not too late to stop climate change, and I cannot emphasize that point more than enough. In the next lecture, we will talk about some of the more wilder ideas out there about how to stop climate change. But when I say it's not too late to stop climate change, it's not too late to stop climate change, and it's not too late to stop climate change in a pretty sensible, controlled way without doing anything particularly stupid. That's the main message of this entire lecture course. Anyway, thank you very much.
Well, thank you for the fascinating talk. That was great. There's been lots of coverage in the last month or so of dramatically out of the norm temperatures in the Atlantic. What does that mean for these models? Does that tell us anything? What did that make you think?
I don't think anybody knows why this particular mode of warm water in the Atlantic has occurred. It's a mode of variability that we weren't expecting, it was. This is all part of the so-called marine heat wave that happened last year. So ocean temperatures were extremely warm last year. Undoubtedly, climate change will have contributed to that. Of course, in other parts of the world, El Nino will have contributed to that. But I don't think we know why. But it's a part of. But we don't know why it's happened. It is a part of the world where there's a lot of ocean variability. So it's not inconceivable that this is a natural phenomenon, and that part, obviously, the component of the warming that's baked in from greenhouse gas emissions, that's going to stick around. But I guess we probably have to hope that this will be that a lot of this anomalous warming in the North Atlantic is a natural fluctuation. One of these wobbles in the overturning circulation and in the Gulf Stream that happens perfectly naturally. Of course, one of the things people do point out is these kind of fluctuations get bigger as you approach a tipping point. And that's actually one of the things that people have pointed out, is that as you get closer to the tipping point, it becomes less and less stable and eventually sort of tips over. And so if we see bigger fluctuations, is it a harbinger of reaching a tipping point? And that has been discussed in the scientific literature. But I think the jury's out on that one. So I'm sorry, I can't give you a very satisfactory answer to that question because we just don't know.
Cool. I'll take one from the online audience, or somebody who may have submitted it in the room. In your opinion, you showed a range of potential tipping points on the slide. In your opinion, which do you think will affect humans the most, or will it be a combination of a number of them?
I mean, to be honest, the tipping points that I think are going to affect humans the most are the ones that involve humans directly. And we'll talk a bit about that both in the next lecture and in next year's lectures. It's when you stress a society and then everybody changes their mind and goes off in a different direction. That's the kind of tipping point. That's the kind of tipping point that I think we're going to worry about well before we have to worry about these ones. So that's the tipping point that keeps me awake at night. And there's plenty of evidence of societies crossing tipping points and moving in unpredictable directions.
With our own feedback loops in the system.
With our own feedback loops in the system. Yeah, you can think about that. That simple model I was showing you. You can replace the terms with, voters and things, and you can see how things can happen quite dramatically.
You said that the ice in, say, Greenland, for instance, would disappear in 10,000 years at the current rate.
At the current rate, very important to stress.
What I was going to ask is, presumably that would slow down at the current temperature rise, at the current level of global warming, would it? And the second related temperatures, at what rate of global warming would guarantee the ice will totally disappear? Yes,
that's a great question. So we obviously have to rely on models for this. It's not something we can experiment with. But the current consensus is that if we sustain temperatures over 2 degrees, eventually we will doom the Greenland ice cap. I mean, you could argue the Greenland ice cap's doomed anyway, because on a 10,000-year timescale, it was going to go. I mean, during an interglacial, the only thing which will save it is another ice age, if you see what I mean. So, but on the other hand, if we push temperatures up by 2 degrees, that's probably enough to to doom it eventually. And the reason is because if you warm surface temperatures, the ice, the surface of the ice itself descends, and as I hope you remember from our atmospheric physics behind net zero lecture, the lower you go in the atmosphere, the warmer it gets. And so there's a feedback effect there that as the ice gets thinner, the surface temperatures go up, and so it melts faster and makes it harder for snow to accumulate to restore it. So around 2 degrees, if you held temperatures at 2 degrees indefinitely, it would probably go anyway. But as I say, it may be. You may be talking about bringing forward the demise of the Greenland ice cap by 5,000 years or something, but it's still a very long timescale process. But that said, so what we're really worried about is not that kind of rather dull dynamics of just the whole ice sheet, but the possibility of large chunks of the ice sheet just going unstable. So in particular, those regions, so the West Antarctic ice sheet, where the bottom of the ice sheet is well below sea level, is if seawater penetrates there, the whole ice sheet itself can be destabilized. And I mean, it couldn't happen in one block, but in principle, large chunks of the West Antarctic ice sheet could suddenly start to break off and drift off into the Pacific, at which point they would melt very rapidly. So that's a serious concern, because that would, of course, drive very rapid sea level rise, and potentially also dump a lot of fresh water into the southern oceans and affect the overturning circulation. So that's the kind of thing that we don't want to happen, and that's the kind of and of course, the warmer we make the planet, the more likely that sort of process becomes, and that's why we're monitoring what's happening in Antarctica very carefully. And that's so probably more so than what's going on in Greenland. I think the news coming out of Antarctica in terms of sort of discovering how dynamic the West Antarctic ice shelf is in particular is pretty worrying.
Excellent. Now, we've had a couple of questions. Actually, we go right back to the beginning of your lecture this evening, when talking about the phases of climate change denial.
Yeah.
And people have picked up a couple of different phases of that to ask you about the communication. So I'll chuck in both questions at the same time. They're slightly different angles on the same thing. So one is about what do you think the key problems are of explaining the level of catastrophic risk related to climate change? And the second one is how can the media reduce the late nature of the climate fatalism of it's too late? So one is right at the beginning of the chain.
Yep.
How do you address that? And the other is at the end of the chain. How do you address that?
I think as humans, we seem to be very bad at getting our minds around planetary scale risks. People almost seem to like it. It's slightly weird. There's a sort of weird fascination with global. Why do we watch disaster movies like The Day After Tomorrow? There's this sort of odd fascination with disasters that affect everybody. I mean, in a sense, I think we find it almost reassuring. In fact, they did public surveys of that film in Germany before people saw the film and after they saw the film, and they found that people actually came out of the film feeling reassured about climate change. And there was two reasons that. I guess one of them was people looked at the film and thought, well, if that's what it is, that's ridiculous. It's obviously ridiculous. I mean, don't worry about that. But the other thing is this message that somehow climate change is something that's going to affect everybody, like a world war, in which case somebody else will deal with it. It's not your problem, which is why I emphasize to people that the real problem with climate change is not these kind of massive global changes that affect absolutely everybody, but the fact that it exacerbates injustices between countries to the point where it will generate, I fear, geopolitical conflict. And this, of course, is looking forward to the final lecture of this series, where we talk about the justice implications of all this. So I think I don't. The answer to your question about how should we communicate this sort of these global threats. I don't know the answer, because I just think we've got a real cognitive problem with even thinking about them. Somehow, as a species, we've not really evolved to be able to comprehend those. But I don't think you need to understand that we can fix climate change. And this is on to the second question. I do think it's very important to remind people, for less than what we paid for gas last year, less than the profits that everybody made in what we paid for gas, you could have captured all the CO2 it generated and put it back under the North Sea twice over. So I keep emphasizing that this is a fixable problem. And that's why people need to recognize that, because that avoids you getting sort of caught into the spiral of doom that a lot of discussion of tipping points tends to degenerate into.
Ladies and gentlemen, the good news and bad news. The good news is clearly we do still have time to address some of the challenges of climate change. Sadly, we don't still have time to carry on this evening's questions. So I'd be grateful if you could join me for one last time in thanking our speaker this evening, the Gresham College Professor of the Environment, Myles Allen. Thank you very much. Thank you.